Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper data structures. In this particular module, we will be talking about another algorithm to find the minimum spanning tree. In the last module, we had already discussed what is spanning tree, what is a minimum spanning tree, which we will again recap in this module also, and we have looked at one algorithm which is the Kruskal's algorithm for finding the minimum spanning tree. So, we are again going to find the minimum spanning tree, but using another algorithm called the Prim's algorithm. Okay. So, these are the people responsible for the development of this particular module, and the learning objectives of this module are to find understand in detail the Prim's algorithm to find minimum spanning trees, and to understand the algorithm through a walkthrough example. Okay. And the terms associated with this module are graphs, because basically we are finding the minimum spanning tree of a graph, what is a spanning tree and the minimum spanning tree, and the Prim's algorithm. Okay. So, before we go further, let us just do a recap of what is spanning trees. So, when you have a graph that is connected, when we visit all the nodes of the graph, it is called a traversal. Okay. So, we have a depth first traversal and a breadth first traversal, where you start at any vertex and we will cover all the vertices of the graph. That is a general traversal. Now, a spanning tree on the other hand is a tree, it is not a graph. The output of we are taking a graph and producing a spanning tree as an output. So, it is any tree that consists only of the edges in G. So, it is consisting only of the edges in tree, and it has to include all the vertices that are there in the graph. So, it consists of all the edges in G, the graph G, and includes all the vertices, but there is no cycle, that is the issue, we will come to that. And also that is a spanning tree. So, an edge of G, that is a graph, is nothing but the edges of the tree and the non-tree edges. So, plus the non-tree edges. The non-tree edges will not form part of the spanning tree, only the tree edges. So, how do you find the tree edges? We will go into that. So, T is a set of edges used during search of that tree, and N is the remaining edges which we do not include for whatever reason. So, basically we do not include edges because it is not among the minimum, or that if you include that edge it forms a cycle. So, the minimum spanning tree for a given graph is a spanning tree of minimum cost for that graph. So, basically we are converting from a graph which may have cycles to a tree which do not have cycles. So, that cycle is an important part of the differentiation between the graph and the tree. Now, let us go to the Prim's algorithm. So, it was initially discovered in 1930 by Wojtek Jarnik, but it was later rediscovered in 1957 independently by Robert C. Prim. So, Prim is the name that is given to the algorithm called the Prim's algorithm. Now, while the previous algorithm that we discussed, the Kruskal's algorithm, starts with is designed with edges, or when you build a graph by selecting edges. In Prim's we start off by picking any node within the graph and we can grow from there. Okay. So, it can start with any node. Now, remember in the Kruskal's algorithm we started with a minimum edge, here we start with any node. Now, you label the starting node A with a 0 and all others with infinity. Now, starting from A, update all the connected nodes labels to A with their weighted edges if it is less than the already labeled value. Now, you find the next smallest value and update the corresponding connecting nodes, repeat until all the nodes have been visited. I will just repeat this once more. You start with a node, okay, and you label it with a 0 and all others with infinity. So, you have not travelled there, so it is in it. Now, from A, you update the label of all the nodes connected to A with their weighted edges. Okay. If the label value is less than, if the weight is less than the label value, if the weight is more than the label value, we do not know. So, the approach to the whole way of building the minimum spanning tree itself is different. So, after you do this, now you have to select the next label. The next label will be the next smallest label, and you select that and update the corresponding connected nodes with the label value. So, you will update it only if the label the weight is less than the already existing label value. So, you repeat until all the nodes have been visited. That is the same in the previous algorithm also. Now, what is the steps of the Prim's algorithm? The new graph is constructed with one node from the old graph, any node. So, you just the new graph is or the tree is constructed with a node from the old graph. While new graph has fewer than n nodes, so you have to account for all the nodes. Find the node from the old one with the smallest connecting edge to the new graph and add it to the new graph or tree. Every step you would have joined one node. So, at the end of that is every step of the algorithm one additional node comes into the tree, and all the nodes it will have the minimum and the graph with the nodes will be a minimum spanning tree of the original graph. So, this is quite similar to the Kruskal, because what we want to do is to find the minimum spanning tree. However, there is one major difference. The tree that you are always the tree that you are growing will always stay connected, but in Kruskal you could add an edge to your growing tree that was not connected to the rest of it. Here you cannot do that, you will add only when there is a connection. In Kruskal's algorithm it depends on the minimum edge. So, you can have two disconnected edges forming two trees, and you could connect the two trees. So, initially you start with all different, remember. So, here you can add an edge that was not connected to the rest of it, but you cannot do that here. So, here is the algorithm. You start with a set which is empty, then pick any vertex from the graph, add the minimum edge incident to that vertex to the S to the set. You continue to add edges into S n minus 2 more times using the following route. Add the minimum edge weight to S, that is incident to S, but does not form a cycle when added to S. So, this is similar to what we did, but the whole data structure is different. So, here we have the Prim's algorithm. You select any vertex A. So, let us assume we select A. Select the shortest edge connected to A. So, that is A B. So, you have 3. Now, you have to start from either A or B and select so A B is selected. Now, you have to start from either A or B. Now, B has 5 and 8 while A has 4 and 7. So, 4 is the one with the select the shortest edge connected to any vertex already connected. So, here we have A and B already connected. So, you have to select the shortest edge connected to any of the vertex. So, to B you have 5 and 8, for A you have 4 and 7. So, you have to select AE. So, AE is selected. Okay. Now, you have BAE. Now, you have to check. To B you have 5 and 8 connected, to A you have 7 connected, which is already not, and to E you have 5 and 2. So, which should you select? You should select ED. So, that is the one that will be next selected. So, now you have selected ED. Now, you have A, B, E and D selected. Now, you have to select the edge that connected to the any vertex already connected, you have to select it. So, you have to B you have 5 and 8, to A you have 7, to E you have only 5, the others are already, the other edge you have already considered. To D you have 4, 6 and 8. So, obviously, which is the one you will select? You will select CD. So, that is the one you will select, or DC. So, since we are having D already, so DC is connected. Okay. Now, you have from C you have 6 connecting F, from E you have 5, from D you have 8, from A you have 7 and from B you have 8. So, obviously, you have to select E5 because that is the shortest. Okay. So, this is the one. Now, all the nodes have been done. So, you have AB 3, AE 4, ED 2, DC 4 and EF 5 and the total weight is 18. So, these are the nodes that you select and this is the way it is done. It is completely different from the previous one, where there we consider only the edges which are whose weights we consider and we add. Here what it may not be connected. So, that is the difference. Here we always start from nodes already present in the tree and try to connect a node to that one, the nodes in the tree based on the minimum value. So, that is the way the Prim's algorithm works. Okay. Now, let us go for a walkthrough. Okay. So, first we have an initial array which contains all the nodes, all the A, B, C, D, 8 nodes, and we have k, that is it is not yet being selected, and we keep the label to be infinity and we have PV, I will explain that. So, this is the initialization of the array that we are going to use for this particular algorithm. Now, you can select any node. So, let us assume we start with D. Okay. We would have selected any node algorithm, let us assume we start with D. Now, what happens, start with any node. So, here we start with D. So, now k becomes true, that means you have visited the node, and initially we label that initial node as 0, that is the distance is 0, and that is it. So, we have not used any edge. Now, what you have to do? You have to select, now from D you have 4 edges C, F and B and E, and out of this C has the, DC has the minimum edge. So, that is what we have to select. So, we take all the edges. So, from D you have the PV gives you the edge from where it you are looking at the thing. So, DC 3, DE 25, DF 18 and DG 2. So, obviously, you have to select G because that has the minimum weight. So, now you are going to select a node that connects to D already existing in the tree with this particular edge. So, I have to select that. Okay. So, that is selected. So, D select the node with the minimum distance. Now comes the updation. Okay. You select the node with the minimum distance, that is over. So, that is what is true. You have not visited the other nodes. Now, next update distances of adjacent unselected nodes. Okay. Now, to D and G, what are the nodes? Now, to G you have 2 nodes H and E connected. So, to D you have H which is 3, and to D to H you have 3G, and to E you have 7G. Now, look at this, in the previous it was E was connected to do D with 25. So, the minimum at that point of time the minimum spanning tree had only D. So, the label of E was 25. Okay. But now what happens, E has been modified, because from D and G if you want to go to E, you could have, you will choose EG and not DG, because EG is less weight. So, that is why we say we change the label depending upon if it is lesser than what was previously available, then we will update. So, that updation is what is happening here. You will see that the updation, this E has changed to 7, nothing else has changed, because G is connected to D, E and H. H is a new thing, new node which is not previously connected to D. So, that remains as it is, but G is connected to E, D is also connected to E. D and E, the label was 25, but now it becomes 7 because this is lesser than 25. So, that is what you have. So, that is how we do the updation of the distance, completely different from how we did it in Kruskal. So, for unselected nodes alone, so that is what we did. Remember, the selected nodes have T there. Okay. Now, you have DG. Now, you have to look at which is the lowest. So, you have you can select either 3D, 3C, C as a node, or you can select H as a node, both have 3. So, what do we select? Let us assume we select the C, that is DC. How do you know where to go? This part you have said what is the source. So, DC is what we have selected, and its label is 3. Okay. So, we have selected the node. So, now what has happened? For the minimum spanning tree DG consisting of 2 nodes DG and the edge 2, we have updated all the distances, and we have selected which node to come in next, and the node that comes in next is C. You could have also chosen H, we have chosen C here. Okay. So, now the minimum spanning tree consists of 3 nodes C, D and G. Now, one job we have to do is we have to add the nodes which connects to C. Okay. So, there are 2 things, C connects to some nodes which is not already there, or it connects to nodes that are there, then we have to check whether you have to select change the label. Now, if you see C is connected to B, it was the previous spanning tree DG was not connected to B. So, B will have the label as 4 and connected to C, that is fine. C is connected to F. Now, F already has 18 there because of the connection to D. Now, that has to be updated to 3. So, that is one change. Then C is that is it. So, C is connected to 3 things, one is a new one and one has to be updated. So, that is what we have. Okay. So, B for C, and look at f, f previously had the value of 18, now it has been updated to 3. Okay. Now, we have the nodes B, E, F and H. Now, we have to check which is the minimum. So, here the minimum is again it could be F or H, whichever one you want to select, it can be selected. So, we have to select the node with the minimum. So, we have to select that. Let us assume that we select F. So, F is selected, over, that process over. Now, we have D, G, C and F collected in that order. How we know the edges? We have D, E, then D, C and C F. Okay. Now, we have to update, right, we have to update from F. Now, F is connected to how many nodes? F is connected to E, F is connected to C, F is connected to B and F is connected to A. Now, some of these are new nodes. For example, A is a new node, E is a new node, E is already there. I mean, it is not yet considered in the minimum spanning tree, but there is a connection there. We will have to update this only if the label value is lesser than what is already existing. So, we have selected F, the next step is to update. So, let us see. Now, from F to A there is no problem, you just add it because there is a new node which has not yet been which is not yet traversable from any other node. So, you have that 10F. Now, what else is changing? C does not come into the picture. F, E okay, changes because previously E value was 7 when it is going from G, but now it is going from F with 2. So, you have to update. Now, look at the other one B, B has 4 from C, as 7 from F. So, that you do not have to consider. So, the two changes you do is you add a which is not yet been considered and you update the value of the distance for E. So, now not only the distance changes, but which node you are going to traverse from also changes. Before it was C, now it would be F. Okay. So, that is over. Now, again you have updated. Now, what we have to do is we have to select the minimum. So, you select the node with the minimum distance. So, the node with the minimum distance now is that E, that is the E with 2. So, you select that. So, that is what we have seen here. Now, what happens? E is a new node. Okay. Now, you have to update with E. The only new node that comes into the picture is, because G is already considered to E and D is considered to E, is B. So, B 10, but B is already only 4. So, update distances, the table entries remain unchanged because of the fact that the B that you have has 10, already it is only 4. So, we do not have to consider. G, D and already been included and E is not connected to any other node except these nodes. So, there is no table entries are not changed. Now, you have to again select a node with the minimum weight. So, A, B and H are the only nodes of which H has the least. So, from G you have to select H. So, that is what is selected. From G you select H. Now, H has to A a distance of 4, while here we have 10. So, now what happens? The dV becomes 4 and the from where you have gone becomes H and not F. Okay. And so, that is what will happen. So, that becomes 4. Now, the minimum you have both are 4. Okay. We will see that the updation. Okay. So, the update distance is there. Now, you have A and B, one going from H to A and one going from C to B. Any of this could have been selected, does not matter because both have the same distance. So, that is what we do. So, first A is selected. So, that is over. Now, the node that is left behind is B. So, select node with minimum distance. So, here again the table remains unchanged. Why? Because from A to B is 8 is more than 4, from H to B is 9 which is more than 4. So, the only way that you want to come to B is through C. I will repeat again. So, this is the updation distances. I am updating the distance of adjacent unselected nodes. There is no change because the only node that you have to update unselected node here is B, and from the node that you have selected now A, it is 9. I mean sorry, it is 8. but already what exists the distance is 4, that is lesser. So, you do not have to change the label nor the where you want to travel it from. So, the final selection would be this, where you select the edge BC. So, what are the edges you have? You have the edges, okay. You start with D, then you have D, from D you have G, and then that is the next one. From G you have H, then from G you have H, from H you have A, from A you do not have anything, but from C you also have B, from D you also have C, and so on. So, the edges are HA, CB, DC, FE, CF, DG and GH. So, this is the spanning tree. No cycles are formed, and the final spanning tree, and the cost of the minimum spanning tree is just adding the distances. So, 4 plus 4 8 plus 3 11 plus 2 is 13 plus 3 16 17 18 19 20 21. So, that is it. So, the minimum spanning tree cost will always remain, but the order in which the edges are taken is different. So, this is, and sometimes if there are edges with same cost, it will have it could choose another edge also. So, this is the minimum spanning tree. You can see from the graph to the tree, the main difference is there are no cycles. Okay. So, what you have done here is you have traversed the tree, I am sorry, traversed the graph, and you have chosen the minimum edges for traversal, and you are in the spanning tree definition you cannot have cycles, and the minimum spanning tree says that you have to choose the edges with the minimum. So, when you the final value of the minimum spanning tree should be the minimum value. Okay. So, how do we analyze the Prim's algorithm? So, the running time is of the order of m plus n log n, where m is the number of edges of the original graph and n is the number of nodes. Now, you could use a heap, we have already seen what is a heap. You could use a heap is for finding out the edges in the with the least values. So, the runtime will be of the order of n squared instead of m n log n. However, using a heap complicates the code, since you use a complicated data structure. Fibonacci heap is the best kind of heap to use, but again it complicates the code. So, it is much more complicated to do, but then if you want if the number of edges and nodes are very high, it is worth going for that. Unlike Kruskal, it does not need to see all the graph at once. This is one of the major advantage. It can deal with one piece at a time. The idea is, if you have a large graph, what do you look at in the Prim's algorithm? You have selected a node, you look at all the edges connecting that node, okay. And it does not need to worry if adding an edge will create a cycle, since this algorithm deals primarily with nodes and not edges. For this algorithm, the number of nodes needs to be kept in minimum in addition to the number of edges. For small graphs, the edge matter more, while for large graphs the number of nodes matters more. So, here again we will just discuss the difference between Kruskal's and Prim's algorithm is basically two. One is, unlike Kruskal you want to see the whole graph all at once, all the edges you should have a picture, only then you can do it, because you always select the minimum edge first and then you have to that is it. Here what it does, it will only be bothered about the node which is there in the tree. So, those two nodes and the corresponding adjacent nodes of those nodes are what you want to see. So, you do not have to see the graph all at once. The second issue is you do not have to worry about cycle issue at all, because here we are not adding an edge, we are adding a node, okay. But essentially the node and the edge connected to it, but still you do not have to bother about cycles. And for this algorithm to work better, in the previous Kruskal's algorithm we said it works better when we have a number of edges is minimum. Here the number of nodes also has to be kept to a minimum. For small graphs it is the edge that matter, for larger graphs it is the number of nodes that matter, okay. And when you compare the two algorithms, both the algorithms will give solutions with the same length. Minimum is not going to change, minimum length or the minimum value of that length, or if you say weight does not matter, and it can select the edges in a different order, that is possible, okay. But still that is again only possible if the number of the edges and all that have same weight and the selection is like that. that is what occasionally they will use different edges also, order may be different, it may even use different edges. This may happen when you have to choose between edges with the same length. So, if you same weight or length. So, if you have two choices, you can choose either one. If there is two choices, it means that more than one minimum spanning tree is available. So, this is what we are talking about. So, basically the Prim's algorithm seems to be better option because of the fact that we do not have to see the whole graph at once, especially when we are talking about applications with large graphs, and you do not want it to be occupying the, I mean you can't afford it to be present in the main memory all at once. So, those issues are there. So, because of that we do not we can use Prim's algorithm, and there is no point, there is no need to find out whether it is a cycle, because when you want to find out whether it is a cycle, again you need the whole graph and you have to keep on checking with, if I add this edge will it form a cycle, if I add this edge will it form a cycle. So, that is not a straightforward way of finding out. As we already discussed, it has to be have a unionizable data structures, which is not a straightforward way. Here also it will be more better if you use a heap, but heap is a data structure that is possible to use with an array itself. Okay. So, in this module we have explained the Prim's algorithm with a simulation to find the minimum spanning tree. We have explained we have tried to bring out the difference between Prim's algorithm and Kruskal's algorithm. Both are both algorithms give you the same minimum weight, both are trying to find the minimum spanning tree, but the approaches are completely different. One uses edges and one uses nodes. One needs to see the whole graph at once, while Prim's does not need to. In Kruskal you have to find whether a cycle is formed when you add an edge. Here that does not arise because you are not adding an edge, you are adding a node. We also explain the Prim's algorithm with a walkthrough example, so that the technique of minimum spanning tree is understood. Thank you.